Friends, welcome to lecture number 6 of Irrigation and Drainage lecture series. In the previous lectures, we were talking about soil water and soil water relationships and what you call this soil moisture content and soil suction. So, and also how to measure soil moisture and soil moisture tension or soil moisture suction. So, so in this lecture we are going to talk about this field water balance. So, once we know measuring soil water, soil moisture tension and within the soil, so then we need to come out and see what are all the inputs to the field and what are all the outputs, and finally, so what would be the storage or the soil water reservoir within the soil system. So, work on some of the problems as well as then how this water balance components. Okay. So, one by one we are going to study. So, if you see this field water balance, okay. So, here, so the water balance has some inputs and outputs. Okay. So, in this picture if you see, right. So, I have taken one element from the soil system, okay, one element from the soil system. So, this is the surface and below that this is a subsurface. Okay. And if you see, there are inputs, water inputs are either irrigation or rainfall or both. Okay. So, then the outputs are here the runoff as output from the element or evapotranspiration. So, if you have crop on top of the soil, then evapotranspiration water is lost through evapotranspiration, and then in the below the root zone. So, this is kind of root zone depth, and then below the root zone you have like a deep percolation loss. So, water can pass through the deep root zone as deep percolation, and then if you have water table lying below the root zone and very nearer. So, then there is a capillary rise from the water table to the root zone. Okay. So, these are the major components we are dealing with in water balance at field level. Okay. So, this is the equation if you see. So, the whole water balance can be written like this. So, SW, this is the soil water, this is the soil water, I indicates in the beginning. So, I indicates the beginning. So, soil water in the beginning plus precipitation plus irrigation plus UW, which is capillary rise, okay, which is a capillary rise. So, these are all contributing to contributing water to this element. Okay. So, this element contributing water to this element, and which is equal to SWF. This is at the, suppose we are balancing daily. So, the end of the day. So, what is the soil water content at the end of the day? So, plus the runoff loss plus deep percolation loss plus evapotranspiration loss. So, if you do not have crop, then and evaporation. Okay. So, soil evaporation, or if there is a water staying on top, then evaporation. So, these are the major components of water balance we are talking about. So, the explanation of each and every parameter is given here. Okay. So, the basically, so in the water balance, so these are the inputs. So, we are giving these are the inputs, and so these are the outputs, and the rest SWI, if you take this SWF, okay. So, here, right. So, the difference is the soil water storage. Okay. So, the here if you bring this here and and inputs minus outputs. So, the difference will give the storage. And next, so the same thing for we are talking about agricultural fields, okay, agricultural point of view. So, the same equation can be, so delta S, as I mentioned, this is the difference between the soil moisture in the previous day and the soil moisture in the current day. So, that is delta S. These are the inputs, input water and output water. So, these are the outputs, and this gives the amount of water which is present in the plant. Okay. So, that is delta V. Since this is less than 1% compared to that. So, we can neglect this in water balance, field water balance. So, and then if you neglect that, so delta S is equal to P plus I plus. So, here D and like the capillary rise and depercolation. So, we have taken the common term D plus or minus. So, it depends the plus D. So, that means adding water from the capillary rise. Minus D, so that is the loss, okay, through depercolation. So, this is the final form of the field water balance. Okay. So, and also if you want to change, if you want to find out the rate of change of moisture storage, that is ds by dt. So, ds by dt is change in P, change in I, change in D, change in Rs, change in Et. Okay. So, this will give the change in soil moisture storage. Okay. So, this picture here represents the root zone, right. This is the root zone, the whole root zone, and then other water balance components like evaporation, transpiration, irrigation, rainfall as input, and runoff or seepage through this is the loss. This is the ponded water. For example, you are talking about rice. This is a rice crop, and then if it is leaving root zone, then it is called depercolation. And the groundwater, so this is the groundwater level. It is called water table, and since the from groundwater table, this is saturated media. This one is groundwater saturated media. So, since this is unsaturated, obviously there is a capillary rise, okay, and the water from root zone will go into the groundwater as groundwater recharge. Okay. So, and then next is how to measure or how to estimate these water or field water balance components. Okay. So, for example, here for measuring precipitation or rainfall. So, the precipitation is a more general term, rainfall is a specific because it is mostly in liquid form, right. Precipitation could be it could be like a general term, as I said, it is a liquid form or snow or hails, drizzle. So, all this come under precipitation. Okay. So, we are talking about rainfall here. So, generally for measuring rainfall we use rain gauges. So, it could be a Simpson's rain gauge, which is a non-recording type. So, in this there is a funnel and a cylinder. So, the water which is collected through the funnel will be collected in a cylinder, and so it will give the cumulative amount of rainfall during the storm event. Okay. And then this is the float type of rain gauge. So, similar to here, there is a funnel here and then a cylinder which has a float, and the float is connected to a pen which is mounted on a drum. Okay. So, the drum has a graph sheet. Okay. So, the drum rotates according to the clock. So, based on the water input to the system, so the pen responds. Okay. So, accordingly you are going to get this kind of signal. Okay. So, this is a recording type, and there is a tipping bucket rain gauge. This is also a recording type. Okay. So, here the same funnel. So, water will be collected through the funnel, and there are so these are the two buckets. Okay. So, bucket. So, this is one bucket and second bucket. So, the bucket which is on top will be filled first. So, once it is filled, it goes down because the weight I mean the more weight here, and this is going to tip the water which is filled here, right. So, it is like a one. So, this is calibrated. So, the one tip contains certain amount of volume of water, and the number of tips will give the total amount of water. Okay. So, this is also it will give either rate or cumulative. Okay. And then simple, there are simple rain gauges, the form rain gauges. So, it is a simple tube and a funnel, okay, and this is pre calibrated. So, this is called 1 inch, 2 inch, 3 inch, 4 inch, 5 inch, and there is a one red float, this is called a float, right. So, you can easily see the water surface here 5 inch. So, this is very simple, I mean a farmer can manage or maintain. So, within the field. Okay. So, the depth of water will be converted into the rainfall depth. Okay. So, this is a pre-calibrated one. So, then the next is, so how to measure the irrigation water. So, irrigation water here using a flow meter. Okay. So, the flow meter as it could be like a like analogy or the digital. Okay. So, so this is very easy flow meter. So, it works on the principle of so the area and the velocity. So, that will give like a number of rotations. The number of rotations will give or turn the needle over here. I mean this is me when I was in UC Davis working in the on the fields, and my colleague Dennis. So, we were using bucket and stopwatch to find out the inflow to the each furrow. So, here like bucket and stopwatch. So, at time 0 time 1 you are going to start collecting water, and maybe for a fixed time interval like 10 minute or 15 minute, and take off the bucket out and measure using the measuring cylinder. So, this will give the flow rate at that particular moment. And then at the field end, so this is the head end, we call this is called head end of the field, and at the tail end. So, this is the tail end, you can say this is the tail end. So, tail end you can also measure the runoff using flumes. Okay. So, this is the partial flume. So, based on the shape there is a calibrated flume. So, based on the depth, so you can convert that into flow rate. So, so this way you can measure the flow rate at the field end as well as the flow rate at the tail end. So, then next is the infiltration. So, infiltration is very important as far as irrigation is concerned. So, the basically infiltration is the water enters into the soil. Okay. So, the process by which water enters into the soil from the ground surface. Okay. So, mainly three forces governs, as I explained in the previous lecture. So, there is a gravity and suction and capillarity. So, these three forces by which water enters into the surface. So, generally we say the infiltration is downward movement, but if I mean truly speaking, the infiltration is a 3-dimensional process. So, it is like so it goes downwards, then it goes horizontal, right, and it goes 2D like radial you can say. Okay. So, the horizontal, vertical, and also the radial kind of thing. Okay. So, that is why this is a infiltration process is a 3D process. Okay. And mainly 3 forces governs, as I mentioned. Then the factors affecting infiltration are the soil and land factors. Okay. So, soil and land factors, the fine soil versus coarse soil, right. Coarse soil, the infiltration will be faster, and the fine soil, the infiltration will be slower. And then land factors. So, land factors, if you have a lot of litter on the surface, right. So, then infiltration will be slower, infiltration will be slower, no, not slower, runoff will be slower, but infiltration not the faster, but opportunity to infiltrate will be more, okay, compared to the bare ground. So, and then the flow conditions. So, what are the flow conditions? Flow condition could be like turbulent flow or laminar flow conditions. So, the laminar flow you get it's a nice flow and calm, a lot of opportunity to infiltrate, compared to turbulent it is very fast, and then it is going to erode, right. So, and the erosion will seal the final pores, and the infiltration will be seized sometimes. And fluid factors, like it is you have the viscosity comes into the picture. So, the temperature definitely influence the viscosity. So, you have a water flow in a cold climate versus water flow in hot climates. Okay. So, definitely when the viscosity is low, then infiltration will be faster. The management practices. So, you have rice soils which needs a lot of puddling, right, and whereas the other crops. So, since the soil is under puddle condition, right. So, the infiltration rate will be slower compared to other soils. So, that definitely, so that is the reason. So, water could stay on rice soils for 4 to 5 days, okay, because of the puddling. Okay. So, the infiltration process, what happens initially, the water enters through the soil, right, through these forces, gravity and suction and capillarity. The first thing what it does, it absorbs. So, the soil particles absorbs water, right, adsorbs, it is not absorbs, adsorbs water. So, all particles are going to stay around. Okay. So, then after that, once that is done, if still the water is falling, then through the gravity force the water will be flowing out. So, then the absorption, adsorption is going to increase, right. So, then gets saturated, then you get gravity flow. Okay. So, and then the gravity flow, the wetting front starts from top to bottom. Okay. So, if you look at this picture, this is all this infiltration process. So, assume that you put some water on top of the surface, then after 1 hour, of infiltration, if you take a cross section or if you take a section of the soil, it looks like this. Okay. So, the first few centimeter you have this saturated zone. Okay. So, this is saturated because there is just right on top of this zone there is a water ponded. Okay. Ponding water is there. Then this is called a saturation. Immediately below that ponded surface there is a water saturation. Then after that this is called a transition zone. So, in transition zone is a rapid decrease of water content with depth. So, here in the other picture it shows the theta, this water content and the depth. Okay, this is the depth. So, water content, this is the initial water content before applying water, this is the we assume that there is a uniform initial moisture content in the soil. Then after that, so because this is saturated, this is saturation point theta s we say, then this is immediately down. So, this is completely saturated. So, that is why the graph starts from here. Then after that at transition zone you could see there is a declining in moisture content with depth. Okay. So, that is what a rapid decrease in water content in the depth. Then after that slow decrease in water content. So, almost from here this we say is a constant up to this. So, this is called transmission zone. So, in the transmission zone if you collect the soil sample, right, and analyze it, the soil water content is almost same, okay, up to this. Then there is a wetting zone. So, this is called wetting zone, okay. This is a wetting zone. So, during a wetting zone, in between wetting zone and the wetting front, so this is a wetting front, okay. So, then after that this is all dry soil, okay. This is all you can say dry soil or initial the soil with the initial moisture content. So, here you can clearly see a decrease in soil moisture, okay, and that is going to connect to your initial moisture content. So, from here to here you get initial moisture content is going to connect. So, this zone is called wetting zone, okay, and this is the wetting front. So, wetting front moves, right, slowly, okay. So, based on the water input here. So, the moment you stop water and the wetting front moves further and going to stop, okay. And then there are infiltration terminologies. If you see here, there is infiltration rate. So, it is measured in mm per hour. So, rate at which a particular soil is able to absorb either rainfall or irrigation. So, absorb water. So, the rate at which the soil absorbs water. So, it is called infiltration rate. Okay. So, it is related to saturated hydraulic conductivity of the near surface soils. Okay. It is almost related to saturated hydraulic conductivity of near surface soils. And the other term is cumulative infiltrations. So, once you have infiltration rate at different time intervals, and you can find out the infiltration depth during that time interval, okay. And if you can accumulate or sum up all the depths, so you get the cumulative infiltration during the period. Okay. This is the accumulated depth of water infiltrating during a given time period. Then infiltration capacity. So, infiltration capacity is the maximum rate at which water can enter to a soil for a given condition. Okay. It is the maximum rate at which water can enter into the soil. So, that is the infiltration capacity. It is also measured in mm per hour. Then the basic infiltration rate. So, this is the infiltration capacity declines rapidly during the early part of storm, then tends to constant value, which is referred to as basic infiltration rate. Suppose if you see, so this is the graph you are talking about and time, and this is infiltration rate. So, initially the infiltration rate would be very high, then after that the infiltration rate is going to decline and then come to a constant. So, this constant, so what we call this is a basic infiltration rate or FC. Okay. So, this is for example, you are thirsty, okay. So, too much thirsty. So, initially what happens, you intake large amount of water, right. Then after that your intake capacity is going to decrease, right. Then after some time you are no longer required any water to drink, okay. So, I mean in your case it is going to reach to the 0 here, but in the soil, in the porous media, and it is all infinitesimally deep, then you may expect the water still penetrate or still infiltrate down, and that is why you get a constant infiltration rate here. Okay. So, then how to measure infiltration? So, for measuring infiltration you have a single ring infiltrometer and also you can use double ring infiltrometer. Okay. So, the infiltrometers are as cylinders. Okay. So, this is made up of stainless steel. So, top open and top bottom open. So, right now here it is showing like 30 centimeter diameter and 30 centimeter we leave 30 centimeter on top, and there is a 15 centimeter below the ground. Okay. There is a 15 centimeter below the ground. So, it could be like it depends. So, right now it is a 45 centimeter this is the deep, okay, 45 centimeter deep and 30 centimeter dia, and there is a scale to measure the water level. Okay. So, initially what happens, we put the water on top, right, and start timing. Then for a particular particular fall, we are going to see the time. Okay. Then we have to refill back and again start counting the time. So that I mean we have to stop the experiment when there is the fall is constant, right, the fall is constant for a particular time. So, rate is constant. So that means if you remember the infiltration graphs, the time. So, we are going to stop this experiment when the rate of infiltration is getting constant. Okay. So, that is the way. So, there is double ring. The problem with single ring infiltrometer is there is a possibility that water can go. We are expecting water should go vertically down, but since it is a single ring, water can go to the horizontal laterally. Okay. In order to stop the lateral flow, so this is we use the double ring. So, the outer ring will protect water from being lost through lateral flow. Okay. So, now we are ensuring that water penetrates down vertically. Okay. So, then in this case, so this is 30 centimeter and this is at 60 centimeter diameter, and similarly as in case of single ring, you have 30 centimeter keep on top of the surface and 15 centimeter down the installation. So, and also here we use the scale to measure the water depth. So, I am going to show you the kind of measurements we made during the experimental ring infiltrometer experiment here. So, this shows the serial number 1 and different times we took this is elapsed time, and this one is interval, time interval. So, 5, 10. So, this time interval. So, I mean this minus this, you get this minus this minus this minus this, like that. And actual reading. So, initially at 28 centimeter, we filled the ring. Then after that we started observing the level to be at around 2 centimeter down. So, if you see this around 26.25, we started we started again adding water and bring it down up to 27.67, this refilling if you see. So, like that. So, you have to count the times 5, 10, 15, 20, 25, as well as you have to add water for a particular fall, okay, fixed fall. Then you have to find out the drop, right, and these are remarks, and this is a cumulative infiltration. Once you know the drop, this is in centimeter and you convert to mm. So, then 9.3. So, this is a drop, okay. This is a cumulative, this is a drop. So, adding these continuously adding this, you get this reading. The infiltration rate is the sixth column divided by fourth column, because individual, and you get the infiltration rate. Okay. So, you have cumulative, you have infiltration rate. Okay. So, once you have that readings with you or data with you, you can draw graphs. This is the infiltration characteristic curves. So, here the time on x axis and y axis infiltration rate, and the other y axis cumulative infiltration. So, the cumulative infiltration goes like this, whereas infiltration rate, as I mentioned, initially it will be higher, then after that it is going to fall. So, you can clearly see the basic infiltration rate. So, here hitting 10.7 mm per hour. So, this is called basic infiltration rate. And then here for sandy soil, sandy loam soil, loamy soil, silty loam, clay soil, different soils, and their steady state is called basic infiltration rate. Okay. So, this is the centimeter per hour. So, this is the data obtained from other sources. So, and then So, next those are the measurements. So, how to estimate? There are some empirical or physically based models available for estimating infiltration. So, here the Green-Ampt, so Green-Ampt equation. So, that is infiltration rate is equal to some Green-Ampt constant plus so this is called porosity, right, and again constant and cumulative infiltration rate, cumulative infiltration, and SE is the capillary suction wetting front or wetting front suction head we call. So, similarly Phillips 2 term. So, this is a sorptivity. Sorptivity is the capacity of soil to absorb water. So, that is sorptivity. So, Phillips introduced this term. So, this is Phillips 2 term, here the cumulative, you can differentiate and you get this equation for this rate. Similarly, Kostiakov equation. So, small f is equal to a t power minus b. So, this is very simple and empirical equation, and if you can integrate that, you get this equation as cumulative. Then Hawthorne model, f is equal to f c f naught minus f c exponential. So, this is the based on the infiltration behavior. So, the equation was, so this is what this is f c, okay, this is f c and this is f naught, right. So, then this is the nature of the curve. So, that is exponential of minus k t. Okay. So, then this is the difference is f naught minus f c. So, from this nature of the curve we fitted this equation. Okay. So, then next is let us in this example let us find out the Kostiakov infiltration parameters, like Kostiakov infiltration parameter small f is equal to a t power minus b, right. So, find out what is a and what is b. So, determine the parameters of Kostiakov equation from the data table 1, table 1 is the previous table obtained during the double ring infiltrometer test conducted at IIT Kharagpur. Okay. So, here the first thing what you have to do is, so in that equation, right. So, this is you have to convert this into logarithmic. So, log f is equal to log a plus or in this case minus b into log t. Okay. So, you have, so once you get this equation, right. So, this one infiltration rate, right. So, convert log f and log t. So, if you have this is a log t and log f, you may have this kind of curve line. So, this is intercept and this is the slope. Okay. So, here clearly you can see this. So, with this you can find out log f value and sorry log a value and b value, and you can convert into you can estimate what is a and what is b. Okay. So, here from this. So, simply it is a fitting. Okay. So, data is given, you fit the data into a logarithmic scale and you get the coefficients. So, once you have that you can use the parameters to redraw it. So, this is observed, the blue one is observed and estimated using the parameters you estimated with the data fitting. Okay. So, the parameters A will be 2.86 and B is 0.487, that is what you got. Okay. So, the next is you can also use the infiltration data to find out Green-Ampt parameters like K and wetting front suction head. So, these two parameters are difficult to find out, right. So, if you have infiltration data, you can still find out the Green-Ampt infiltration parameters like here the K and, so here sorry, here K and psi. Psi is the wetting front suction head. So, but only thing, the tricky part here is, so you have to do the experiment 2 times. So, first is like ring infiltrometer with 6 centimeter ponding depth and 12 centimeter ponding depth. Okay, for 6 centimeter ponding depth, so the time and cumulative and infiltration rate. Therefore, 12 centimeter you have cumulative and infiltration rate. So, you need these two data sets. So, once you have two data sets, the other thing is, so this is the equation, the Green-Ampt equation. If you see, small f is equal to k plus delta theta and h plus psi by f into k. Okay. So, delta theta is theta s minus theta I, which is saturated soil moisture minus initial soil moisture, okay. And h is the ponding depth and psi is the wetting front suction head and k is your Green-Ampt parameter, or you can also some researchers also use as a hydraulic conductivity. Okay. So, the interesting part is, so this equation did not contain T term. So, clearly see there is no T term here, right. So, absolutely no T term compared to other equations. In other equations, so the time term is there. So, that is why this is called autonomous equation. So, the solution is difficult. In other case you get the solution in analytical solution, but here you get the numerical solution. I mean iterations only you can find out the infiltration rate. Okay. So, what you have to do here is, so if you observe this equation, so f is equal to k plus 1 by f. Okay. So, let us say, so f is equal to let us say a plus b by f. Okay. So, this is a straight line equation. F, if you have f versus 1 by f, the curve the line, and this is the intercept and this is the slope. So, that is the idea here. So, you have capital F, you have small f, and find out what is 1 by f. Okay. Then this is of course, once this is finally once you have the k and psi parameters, you can estimate. Okay. So, and you can compare observed and simulated. Similarly, for 12 centimeter you can have f and 1 by f. So, small f and 1 by f. Okay. Once you have these readings, so next part is drawing the graphs. Okay. So, you draw the graph here 1 by f versus small f. Okay. So, you have a straight line, and this straight line, this is the, you have to fit the dots the straight line equation. So, this f is equal, you get this regression equation. Similarly, here for 12 centimeter ponding depth, you get this regression equation. Okay. So, you have two equations now. Okay. So, two equations and also two unknowns. Okay. So, if from this equation, from these equations, if you see so for 6 centimeter you get 0.017 the k value, and for 12 centimeter 0.0107. So, they are close, right, the k values are very close in both cases. And once you have the k value, right. So, once you have the k value, if you remember the equation, f is equal to a plus b by f. So, where a is equal to k plus b is delta theta into h plus psi, okay, into k divided by f. Okay. So, k value is known now, this is known. So, unknown term is this part, this is unknown term, right. So, here this is unknown, but within the unknown terms the psi is unknown, and delta theta, which has theta s minus theta I. If you have this data, you can easily get this. Okay. So, if you do not have the data, then theta s also need to be estimated, and you may have to go for another set of data. Okay. So, 3 unknowns, 3 data sets. So, then so psi is, so since k is known, right, and 2 equations, you can find out psi easily. Okay. Okay, so here in this example, I mean the continue to the example. So, for 6 centimeter ponding depth, so this is the equation we got, right. Delta theta h plus psi into k is equal to this much, and delta theta, so h is 6 centimeter psi, and you get finally. So, this is the delta theta 6 plus psi is equal to this much, and if you follow for 12 centimeter ponding depth, you get delta theta 12 plus psi 0.55. Okay. So, the two equations, okay, in the two equations you can find out the psi value as well as delta theta value. Okay. So, delta theta value you can find out, and psi value you can find out, and k value you have already known, and delta theta, if knowing knowing the I value, like initial moisture content. So, when you start the experiment, take the soil sample and analyze it. So, that you get, that is theta I. Okay. Then you can easily find out what is theta s using this value. So, this is the advantage with ring infiltrometer data. So, with ring infiltrometer data you can estimate Green-Ampt infiltration parameters. So, that is the physically based, that is physically based. So, you can also get physically based the physical parameters like k and wetting front section head, and also theta s, right, using this. Okay, so that is all for this lecture. So, in this lecture what our focus was the field water balance. Okay. So, this contains inputs and outputs. The inputs are here rainfall and irrigation. Okay. The outputs are runoff, evapotranspiration, depercolation. Okay. So, then when you subtract outflow from the outputs from the inputs, then you get the change in moisture content. Okay. So, and then we started digging how to measure the precipitation or the rainfall in our case, and then how to measure infiltration, then now how to estimate infiltration, then how to measure irrigation. Okay. So, then how to estimate Green-Ampt infiltration parameters, how to estimate Kostiakov infiltration parameters. Okay. So, then we have also seen some of the equations used for infiltration estimations. In the next lecture, we are going to talk about the evapotranspiration. So, that is another component of this water balance. Okay. Thank you so much.